All right, so we have today's lecture is about autonomous particles and emergent fields. This is something we only wrote about recently. It is related to many branches of machine learning, but so far we only applied it to reinforced learning in context of the autonomous driving. Now, but the idea is very broad. It's usually, as usual, borrowed lots of things borrowed from physics. And as I will argue, this setup is not only useful for us to develop machine learning algorithm, but we can reverse it and actually use the learning theory to model physical and biological, and also biological systems. So if that's what your project would be, I guess you should pay attention to what we're going to discuss now. Now, what's the idea? We will first start with discussing what the symmetries are and why knowing the symmetries ahead of time is useful. Sometimes you don't know what the symmetries are, and then you have they're not apparent, and so you want to perform some tests on your training data set to uncover them. But once you do see them, you should make use of them. Now, here's a general statement that what we're interested to see is the symmetries in the boundary dynamics in your training data set. Now, what it means that, well, basically you have your probability distribution or a distribution over paths, as we discussed, is equal to, it doesn't change as you perform a transformation. But in this case, S describes transformation, and it's only transformation of the boundary neurons, the neurons that describe your training data set, whether they are input or output neurons, it doesn't matter. Now, it can be a linear transformation, then I would put here as hat, it would be kind of a matrix, or non-linear. Whatever that is, uncovering and learning what this transformation is essential. Now, why? Well, here's the main idea. If you do see that the probability distribution doesn't change, then the directions along which doesn't change are not something you should learn. Not something you should worry about. Now, even if you don't know about those directions, eventually your learning system will uncover them. But maybe you can help it. You can design your neural architecture such that it respects the symmetries. Now, a good example of that is convolutional neural networks. And because when you use convolutional neural networks, for example, for image recognition, you know that there is a shift symmetry, there is rotation symmetry in some cases, and also sometimes you even have a scaling symmetry. And if you do have that, then maybe you should incorporate it in your structure, in your weight matrix. Now, that reduces the space of the trainable parameters, and it allows you to train your neural network faster. Now, for the images, maybe it doesn't matter where a given object appears on the image. And so whatever you do, you should make sure that the architecture is insensible to those shifts. Now, however, this doesn't apply to all neurons, because your training data set only tells you that the boundary neurons, the image, has the shift and rotation symmetry, and there is no need to have the symmetry respected as you go into the bulk. But however, when you use convolutional structure, there is that symmetry. Moreover, there is the scaling symmetry that appears, hierarchical structure of the weight matrix. Now, for today's lecture and for the results of the research that I'm going to be presenting, the only assumption that is made is that there is some kind of training data set. It has symmetry, and we only want the probability distribution to be invariant under the training symmetry of the training data set or all the boundary neurons. And we will not be extending it into the bulk. There is no need to believe that this symmetry should be preserved in the bulk. And in fact, there is some research that was done that shows that it is a mistake for convolutional structures to extend this into the bulk. But this is a preliminary result, and we'll still have to do more analysis to confirm that. Okay, very good. And now, what does it mean that we want not to have any symmetries preserved in the bulk? It means that the network has to be unconstrained. So we should not be putting into the bulk architecture of the neural network something that is not needed. And so you leave it unconstrained, and all of the constraints comes from the symmetry that you observe in the boundary. So let's have an example of all what I just said. Oops. Oh, it doesn't go. Okay. Yeah. So reinforcement learning. So what is it, and how is that related to symmetries? Where are the symmetries there? So consider a task where you have an environment which describes your boundary dynamics or training data set. And let's assume that it has lots of information. We're not talking about symmetries yet. We just know that there is a lot of information in the environment. A self-driving car goes around the roads, and there's a lot of information goes towards the car, and the car has to somehow interpret it. Presumably, neural network has to be trained to interpret it. But then at the end of the day, there are very few actions that the car can take. It can, put the steering wheel position in a certain place. It can brake. It can accelerate, and that's about it. What does it mean? It means that the car has to, the neural network of the car has to be trained such that it maps a lot of input parameters describing the environment into the very, very few parameters that describe possible actions. Now, that suggests that there is a lot of symmetries. Well, only that already suggests a lot of symmetries. The very same actions would be performed for very different states of the environment. Now, what those symmetries are may be a challenge to discover, but some of those are apparent from the problem. When you look at the boundary, you say, well, maybe it doesn't matter whether I'm traveling, south or north. If I see exactly the same picture around me, my action should be very much the same. So maybe there should be this rotational symmetry, or shift symmetry, or temporal symmetry. So maybe there are some symmetries that you can identify ahead of time, and if you can, then use those symmetries to building your architecture. There will be many more symmetries that you will not discover, and so the neural network would have to do it for you to discover those symmetries, but at least help the neural network to do it by starting with some symmetries. And so what we're going to have here, we're going to identify some symmetries of the boundary dynamics. In particular, we're going to be identifying the Galilean symmetry. Now, Lorentz symmetry is just another example that at some point might be relevant, but it's not relevant for the self-driving problem, so you wouldn't have to worry about this one. Now, the identification of symmetries, you can think about as a coarse graining of information. So yes, there is a lot of information about the environment. Lots of it is irrelevant. So you call those irrelevant directions as symmetry directions. You coarse grain over them, and then whatever is left is the relevant information, information that you would be using for training your neural network. Now, this flow of invariants or operators is usually called as a normalization group flow. However, in our case, all that we are going to be referring here is that let's just identify the invariants that are useful. We should think about them as relevant operators in context of a normalization group, but those details are not needed for us. And sometimes it will be a challenge for us to identify what is the right invariant. And so we'll play with few. We'll play with few and we'll see, okay, well, both of them make sense. Let's now go to experiment and let's see which of the invariants would be useful. Now, however, some of the invariants will be disqualified right away. We just know ahead of time by looking at what they are, they would be disqualified, and we'll say, well, no, we shall not use them. And that's kind of where the art of designing a computer architecture would come from. We know that there should be invariants, but we don't know which ones. And so let's use some ideas from physics to identify which invariants are more useful, which invariants are less useful. So that's the setup. Question about the setup. All right, so now before we actually go to the problem, let me spend some time explaining how this appears in the electrodynamics. I'd like to make a connection from the problem of self-driving cars and electrodynamics. So one is completely separated problem of machine learning, and the other one seems to be just physicists would be concerned about. But the two are actually showing us the two possible ways of thinking about either of the problems. And what I'll argue for is that you can take machine learning task and apply the tools of physics to study it, or you can reverse it and say, all right, what about if I have physical theory? Can I use some of the machine learning techniques to study it? And then the answer to both questions will turn out to be yes. So I will be talking about electrodynamics, which means, electrons move in the electromagnetic field, but you should start thinking about those electrons as if there were some autonomous particles, some neural networks that are making decisions of where to move, where to accelerate, how to steer their wheel, and where they will have to make this decision. However, we are not going to be approaching this problem from the point of view of machine learning. However, and we'll first show you how it's done in physics. And once you know how it's done in physics, we'll be able to connect the dots and apply the same technique to study the problem of self-driving. Okay, so we start with a charged particle. Now it can be an electron for what we're about to discuss. Now it's moving in an electromagnetic field. So there is an electromagnetic field. For the example that I have below, I only assume that there is electric field. I make assumption that there is no magnetic field, but this, of course, can be easily generalized to have both electric and magnetic field. Now, for a test particle, or for this autonomous particle, at any time t, in order to make decisions of where to move, all it has to do is to determine the values of electric and magnetic field at its location. So it may not know anything about other particles, but it just looks for electric and magnetic field. And once it knows it, it knows how to move. And usually what we would have to do, you plug in this E and B into the formula for the Lorentz force, and it will tell you how to move. Now, what's important is that this E and B field for the particle at the position of the particle, or the position of this autonomous vehicle, if you want, in order to figure out what this E and B fields, they're actually generated by other particles. Okay, so all other particles and its surrounding generate this electromagnetic field, and then this electromagnetic field travels to the particle in question and then gives value to those fields. Now, E and B are just triplets of numbers. So there are 3 for E field and 3 for B field. You can have many different configurations of other particles moving around, but at the end of the day, only 6 real numbers will determine where the test particle, this test vehicle, if you like, will move. So most of the information about all other particles had been coarse-grained. It is irrelevant information, and only very little information is preserved. It's only 6 real numbers. So there are many different configurations of other particles that are completely different. If you look at it globally, give rise to the very same electric and magnetic field. That's important. This is coarse graining information from the point of view of that particle that is deciding where to move. That is coarse graining. This is just paying attention to only a handful of relevant parameters, which are encoded in E and B. Now, let me show you how it exactly works for the case of electrostatics. Electrostatics is when we assume that the particles are all stationary, they're all in some positions. Their velocities is very small if there are any, and there's no magnetic field at this point. just to illustrate it. Whatever I do here can be easily generalized to having magnetic field and to have particles in motion. It's all will be consistent. So now, how do we calculate the value of the electric field, the value of that relevant parameter, if we know the locations of all other particles? Well, for that, we solve Maxwell equations. And here I just choose two Maxwell equations. One that tells you this electric field has to have divergence equal to the density of the particles. Now, if the particles are discrete point-like objects, then this rho will be a sum of delta functions. So it's either 0 or a delta function. Now, the other condition is that comes from the fact that there is no time variation in the magnetic field is this cross curl of E equals to 0. Basically, usually we would have here is dB dt, another term here, but since we assume that there is no magnetic field, there is no other term. So this is the only thing. So those two equations determine what is the electric field is everywhere in space. Okay, and that we claim is the relevant parameter, and that is the relevant information about location of all other particles if the particle is to move according to electromagnetic field. All right, so now how do we decide how it moves? Well, first we solve those equations. Now the second equation, curl of E, tells us that E has to have this representation. So there exists a phi, which is called electric potential, whose gradient equals to E. Basically, if you take this gradient and you put it here, the curl of a gradient will give you 0, and that's the reason why there must exist this phi, this field, the electric field. Okay, so now once I have this, I can plug that into my first equation. I'll get divergence of the gradient, which is Laplacian of phi, equals to rho. So this is an equation of, we have a three-dimensional Laplacian equals to rho. Now, the way you usually solve it is you apply Green's function method. What it tells you, well, don't worry about that problem, but solve another problem where you have a Laplacian of phi equals to a delta function. Obtain solution for that equation, and then solution for equation phi will be just equal to the integral over the entire space, where this is now your Green's function, which you solved, multiplied by rho. Okay, so now, so this is phi. I will argue that this is the only relevant information about all other particles, at least in this electrostatic limit. And it is given by the global integral of the density of all other particles. Again, think about them as cars. Of course, we'll be using different Green's function here, but at least this is a good illustration of what will happen. And then you integrate it by multiplying by this Green's function, this 1 over 4 pi x minus x prime absolute value with a minus sign. So x prime is the location of all other cars, you may think, and then x is where you are, where your car is sitting, where your autonomous particle is sitting, which is trying to figure out how to move. And the way it moves according to Coulomb force, and the Coulomb force is nothing but Q, which is some arbitrary constant here. Usually is the charge, but here it's just some constant that describes how sensitive the car should be, or this autonomous particle should be, which in this case is electron. And then if it was an electron, then Q just would be equal to E, negative E. Okay, so now the force applied to the particle will be proportional to this E. E, we know electric field is a gradient of phi. And so this is our expression. And the phi we just found. We found this expression, which we say is the only relevant invariant that is there. Okay, now we plug it in. And so we still need to take a gradient of it. But at the end of the day, this will be the expression that will tell us where to move. We'll tell how to, for the electron, how to move in order to respect the Coulomb force law. Okay, now we didn't start here with any objective for the electron. We started it with the force law. We say, okay, here is the force law, which is Coulomb law, Coulomb force law. More generally, with the magnetic field, it will be Lorentz force law. And we started with the relevant invariance, which was this phi. Now it was relevant for so the invariance form of the invariant would be described by Maxwell equations, but the way the particle moves was described by this Coulomb force or Lorentz force in general. So that's the setup. There's no learning objective. We haven't identified a learning objective for that particle, and so that's only one view. The other view that we will suggest will be the opposite, in a sense, will be dual, is that instead of identifying the force law, we'll be identifying the objective for the particle. And then we'll be calculating what should be the force in order to optimize this objective, but that will be next. So for now, let me ask you if there are any questions about the electrodynamics, how that works. In summary, you have a distribution of charges. They generate this electric field, and then that field is used to determine how the charged particles move. Are there any questions?
What are the 6 numbers here?
Oh, E is a vector, 3-dimensional vector, so there are 3 numbers for it. And B is a 3-dimensional vector, so 3 numbers for that. However, in the case of electrostatics, instead of 3 numbers, there's no B, so those 3 numbers are gone. Instead of E, you actually have only 1 number, a scalar field phi, electric potential that determines everything. So to generate the motion of a particle according to the Coulomb force, you only need 1 number. 1 number is this, phi. So phi completely tell you at the location of the particle where to move. You calculate phi, you take it, well, maybe phi and phi in the nearby regions, right, around. So you want to take a gradient of phi. But nevertheless, this will be enough for you to determine where to move. So that's your invariant. This is something that you've locally electron discovers, calculates. Now, how does it do this? Well, what it can do, if it was a car, right, it would scan around, find location of all cars around it, then it'll perform this integral, which is very easy to do. And then once the integral is done, it knows exactly what phi is. And so it knows where to move.
I see. Thank you.
Sure. Okay, but we're not constrained to have 1 invariant. We can have 1, 2, 3, 4, and especially when we're not sure what are the relevant invariants. So you will see invariants of that form in what follows. Now, the reason it's invariant is because this is absolute value here. So it only depends on distance between the two. It doesn't depend on what I decided to call the origin. Okay, so let's move on. So now, before we actually go to the algorithm and describe how this neural architecture should be constructed, I will once again go through those 2 dual pictures. And they're both of them, either one of those 2 pictures is useful. And it turns out that usually in physics we use one, and machine learning we use the other. But if we see that they are the same, then they can help each other. You can use one view to study the other system. Local view, okay? You have particles or cars. They emit some field. In this case, it's electromagnetic field. But in the case of self-driving cars, it will be some other field, auxiliary field. They emit particles, and this field contains all the relevant information. Okay, and so once you receive all this information in this field from all of the particles, you calculate your local field, and then this local field tells you how the particle should accelerate, the strength of that field, nothing else. Now, why I call it a local view? Well, because I locally measure the electric field, and also all other particles, all other cars, all other autonomous vehicles had also been emitting that field locally. Okay. Now, because the speed of light is so fast, really, once you emit a signal, it comes right to the, spread out through the entire space very fast. But nevertheless, the theory is local. a car locally emits field, and the car locally observes the field or calculates the field, and then uses the field to move. That's a local view. This is a view that is comes from physics. This is how physicists construct theories. Then they say, okay, what should be the local law of emitting field? That's Maxwell equations. And what should be the law for once I have this field to move? And that's Lorentz force law. So it's determined. Experimentally, was determined what are the two laws are. Now, the global view is different. The global view is more commonly used in machine learning, where you think that, or self-driving in this case, you have a particle that is, using its cameras to detect the state of the environment, global environment. So it knows the position of all cars, of all other obstacles. So it scans it globally, and then calculates some relevant information, and then use this relevant information to move. Now, if the car was to move according to the Lorentz force, then the relevant information would be exactly the electric and magnetic field. But in general, this global view can be something else, and there may be some other relevant information that is not the one that I wrote on the previous slide. And as we will see, it will be different from this. So the invariance will not be this. So we're not expecting that self-driving cars will behave like electrons or anything like that. But those are two pictures, right? You think about the fields, or you think about locally scanning everything and then determining the relevant invariant. The two pictures are actually not very different, and let me now go through this in a deeper way. Now, instead of only talking about electrodynamics, let's just generally think about how physicists think about the problem and how machine learning scientists think about the problem. So physicists, if you give it some particle bouncing around in the box, according to some laws, what the first approach would be, well, let's look for Lagrangian. Let's look for Lagrangian, which I will vary and then obtain equations of motion. Obtain equations of motion for fermions, for those particles, and also for bosons. And bosons are the ones, so you think about fermions as autonomous particles, and bosons as the field that gives rise to this relevant invariance. That's physicist view. You wouldn't have to, it doesn't matter what really happens, but this is the analysis the physicists would do. You have particles, let's write a Lagrangian. Fermionic Lagrangian for autonomous particles, and then bosonic Lagrangian for this relevant invariance. And there'll be interactions between the two, because we do want the bosons or electromagnetic waves to be emitted from those autonomous particles. Now, machine learning view would be, well, don't start with a Lagrangian, but start with a loss function. Well, try to figure out what is the learning objective of those autonomous particles. It doesn't matter that they may be just electrons, and maybe somebody will say, well, don't think about electrons as a learning task. But it doesn't matter. You still see a box, you see things move, and you're trying to figure out using the tools you have. And so for machine learning people, it would be loss function. And then the machine learning engineer would look at this and say, all right, so let's try to figure out what are the relevant invariants. Now, invariants are, again, something that you would have to convince yourself first that you should only look in the invariants, but that comes from the fact that you do want to help out the neural network to study only invariants, because if they're not invariants, they're not useful. They're not providing any useful information about the system. Okay, so physicists view write down Lagrangian, machine learning view write down loss function. And those two views are completely equivalent when it comes to modeling, because at the end of the day, what you want to look at the system and try to predict how it will behave. Now, either one of them can be used. So you can use the local physical view to help develop machine learning algorithms, or you can use the learning view to help develop field theories. And in the case of the machine learning, if you have a machine learning task like self-driving, and if you follow this path and you see that the two views are the same, what you will end up with some field theory. And so I would say, well, then the field theory emerged. There were no field theory. There were self-driving cars. The or even not self-driving cars, the actual driving cars. There were people driving around, and then I would model them through the fields, because that's kind of a useful language of modeling such systems. And then I would say that the fields emerged from the dynamics. There were no fields to start with, that they emerged because they describe correctly the relevant invariance information. And you can play the same game with the physical theories, right? You can look at the physical theories that would be inspired by machine learning. Maybe you will start with a loss function that you think is useful for accomplishing certain learning tasks. You will train your system to follow those loss function, and then you will study what kind of useful invariance your field theory contains, and then you will uncover a new field theory. So I don't know what the field theory is for full self-driving cars, but I already know what the relevant invariance, and so that's one step in that direction. And once I take this step, then I can complete this and get from the learning objective, from the loss function, to Lagrangian. And so here are the two languages, right? So you want to start with Lagrangian, go ahead, but there must be some learning loss function there. If you want to start with a loss function, also go ahead, but there must be some Lagrangian description at the end of that. Question. Okay, so now let's dig into the particular example. So we already showed the physical system, electrodynamics, where things, ideas work well. Now let's go and try to uncover how this may help us to derive self-driving cars, right? Autonomous driving. And we'll be not chasing the real world. We are trying to identify what are the important principles underlying self-driving or autonomous driving. Now, usually you can divide the problem of self-driving into three parts. The one part is environment detection. So really figure out where all the other cars are, figure out where all the obstacles are, figure out what the road signs are, people, you name it. And the second problem, once you have this all information, make a decision. How do you want to move? Again, there's lots of environmental information, and you have how to coarse grain it and make a decision based on the like how to steer your wheel, or how to accelerate or brake, accelerate or slow down, right? Now, of course, you may know how you want to go about acceleration, and you may have a prediction of where you want to be at the next moment of time, but the vehicle may misbehave, right? So there may be a slippery road, something may happen. And so the mapping from whatever decisions you made to what actually the car will do, there is still this missing gap, right? There is a missing layer. We call it technological layer that would have to be implemented. And so there are three things, basically. You have environmental detection, you have to make a decision, and then you have vehicle control. So for this talk, we'll make assumption that environmental detection was solved. Whatever techniques you had, you know exact location of everything in your surroundings. Furthermore, we'll simplify things, saying that your surroundings, your environment consists of only cars and nothing else. And moreover, I'm going to treat all those cars to be of the same type. So I'm not going to make an assumption that people owning red cars are usually faster drivers, or whatever. I don't know if this is true, but maybe. So they all be the same particles from the point of view of making driving decision. And I will also assume that when I determine the desired position and velocity in the next time step, I can accomplish that without problems. Yes, there'll be constraints on the vehicle, so it cannot go too fast, it cannot accelerate too fast, but all those constraints are something that I have under complete control. And of course, as I said, in the real world, you would have to also train for this technological layer in making sure that the car gets the velocity and gets the acceleration that it wants, and then you know exactly how much to brake and how much to push the gas pedal in order to accomplish that. Okay, so now vehicle control solved, environmental detection solved, decision making, the hardest one. You still have lots of information. You have a lot of cars around, and all this information we know has to be compressed. It has to be coarse grained. Why? Because there's very few things you can do. You can just steer the wheel and brake or accelerate. So we know about that, and we look for the symmetries, and some symmetries are apparent. They just come from the fact that there is a Galilean symmetry of physics, right? So we know that your laws should not depend on the rotations or shifts; they are the same everywhere. So we should be, if we are to compress information about the coarse-grained information about the environment, what we have, maybe we should just stick with the invariants, because if they're not invariants, then it would be unusual that you would make different driving decisions in different places. Now, it's not completely true, because you may be making different driving decisions, if you drive in New York or in Minnesota, depending where you are, but we're ignoring all those problems. Okay, so now let's talk. So this is a setup. So in this neural architecture, you have a detection layer that detects position of all cars and velocities. Then it forms some number of invariants, very small number of invariants. So there is a lot of information here. There's little information here. And then it uses the completely unconstrained neural network. So we don't want to put any constraints here, because if you put some constraints here, it means that you're making assumption about the symmetry that may not be there, and that may slow down learning. Okay, so there's no constraint here. And then at the end of the day, what it gives you out is the desired velocity and position of the velocity in the next moment, of the car in the next moment of time. So we assume that we can accomplish that. Yes, there'll be constraints on the velocity, but we can always get that. And so the technological layer we always know by how much to steer the wheel and push the gas pedal in order to get to the desired location at the next time. Okay, now for this blue type, part of the network, which we're interested in, the inputs will be all invariants. Okay, so there'll be nothing but invariants here, and I'll show you exactly what they are. Output will be position and velocity of the car, as I already said. Now, for the learning, loss function will also be built out of invariants. These invariants will play a different role. They'll be trying to accomplish different tasks, but their whole loss function will be built only of them, and there'll be a small number of them, only 3 invariants. And the activation is unconstrained. As I said, we use this ReLU in here. There are only 30 neurons, so it's very, very basic system, and then we'll see how it's actually able to perform and drive. Okay, so that's the setup, and let's list the invariants so that we know what they are. This choice, the choice of those invariants was not completely random, and there's some thought behind it. But from the point of view of what we are doing here, you may play with other invariants and then also see that some work better, some others don't work as well, and there are reasons for that. You can actually look at the invariant and say, okay, it wouldn't be doing what it should do, and we actually learned some of those things the hard way. Okay, now the symmetries will try to respect Galilean symmetries, so things shouldn't change on the rotations, on a translation, so there'll be no roads, because if there were roads, then Galilean symmetry would be broken. There will be preferred directions of where you should go, but for now we are assuming that all those invariants or symmetries are present. And then also permutation symmetry, assuming that all cars are of the same type. We are not making assumption. Now the system can potentially learn, like in more complete form of this model. You could have many different types of cars, right? The cars describing the parked cars, the cars describe trucks, the cars that describe buildings. I mean, also some kind of stationary cars. The particles that describe these road signs. All those things could be added without adding a lot of complexity. The number of input invariants will still be very small, and so the system could still learn how to treat all those different invariants in the correct way. Now, what are the 2 objectives we'll try to accomplish here? So the first one is we want cars to go to their prescribed destination. We'll be choosing random destinations, and then we'll say, okay, car, it's your objective. You want to get there as fast as you can. Okay, and then this is the invariant will be responsible for them. This is the first one. Why is it invariant? Because you have velocity dot product with a position vector. So in the result, you get a scalar, and the scalar is invariant. And moreover, you divide by the absolute distance, absolute value, which is also a scalar. So any scalar with respect to the symmetry transformation is an invariant. We'll also add this term. This term tells you that we want to have a maximum speed to all cars. They should not exceed the speed in here in those units. The speed of maximum speed of cars is 1. So just arbitrary parameter. So go to your destination, but don't go faster than 1. So going as fast as speed 1 is okay, but don't go faster than. All right. But what else? The other objective is not to collide. Now, if this one is a kind of interaction with the destination, so this is velocity, capital V and capital R, velocity and position of destination. U and R are the velocity and the position of a given car alpha. Now here you want to avoid collision with other cars. So for your car, the car at position rho alpha has to avoid being at the same position with the car beta, rho beta. So when this goes to 0, this term blows up, becomes very, very large. And so you will see that this term will make sure that the collision are avoided. So cars cannot come closer, should not come closer to one another. Now, they may actually collide at some point just because your predictions are not perfect, and it may happen that especially in the early stages of training, that you want to able to predict that this scalar, this invariant will blow up, and then you end up colliding. But with training, you will make sure that this remains small, so rho alpha is never in the position of rho beta. There is another term which also describes interactions between other particles and also avoids collisions, but here it also depends on the velocity of the respective velocity. So are they going towards each other or going away from each other? So maybe if they're going towards each other, being too close is very bad. But if they are moving in the same direction, then even if they're close, this is not so dangerous. So, cars can move along the same road in the same directions, and they can be very close, and that shouldn't be too harmful. That's it. Only 3 invariants. Get to your destination, avoid collision, and moreover, avoid head-on collisions. And those are the 3 invariants that would be used as inputs to the neural network. And those are 3 invariants that will form the loss function. So we want to make sure that it does get to the destination, avoids, doesn't stay too close to other cars, and definitely avoid head-on collisions over. And that's it. That's the only setup. And I will see if there are any questions about those 3 invariants. It's only 3, so 3 input neurons. Any questions?
Sorry, what is U in the first invariant? U alpha?
Yeah, so U, it's your velocity, right, of your car. V is the velocity of the destination, so it doesn't have to be even stationary. So everywhere we see U and rho, it's velocity and a position of a given car. And capital V and R are the velocity and position of destination where you're trying to get.
Okay, and then so this makes up the loss function, and then you're assuming that similar invariants are learned by the perception system, so that's a given.
Right. So yeah, it's a very good point, because we are kind of using the very same invariants in the loss function and as input to the neural network. So the kind of invariants play the dual role. They play a role, something that you want to minimize, but since you want to minimize it, it is the relevant information, right? And so since it's relevant information, make use of it in order to determine where to go. And so and from the point of view of this plot here, those are the invariants that will be here in your invariant layer. And then those invariants that will be used to calculate where should you go, how you should steer the wheel. So very basically, only We have very few, like 3 input neurons and very few output neurons. Yeah. Okay, so let's see how.
Excuse me.
Go ahead.
I have a question. So
Mhm.
this is not what the relevant invariants come down to for electrostatistics, right? Because it's a
Yeah, in
completely different.
electrodynamics, you had some different invariant here. So you had 1 over x minus x, remember? So that was,
Yeah.
and then you took a gradient. So actually, once you take a gradient, it was 1 over second power. So that's what was in electrodynamics. So similar to this one, but not to this one. But remember, in electrostatics, we had stationary cars. So for the simple demonstration, once you include motions and the velocities, you will see terms like that appearing there as well.
Are like there any effects of quantum mechanics in
Nope.
previous case, but not here? Like
There's no quantum mechanics here either. So there's no quantum mechanics. It's all classical.
oh, okay, it's just
So
classical.
yeah, quantum mechanics is a difference, right? No, everything classical in both cases, just two different views, right? So in one case, you have some, bosonic field that goes around the electromagnetic field, and the other one, car itself calculates what the bosonic field. Now, it's interesting to note that actually it is the electromagnetic field that comes to cameras of the car, and actually that electromagnetic field is actually used to determine position of all other cars.
Yeah.
But we take that information about that field and construct different invariants from it. Yeah.
Okay, I see. Thank you.
Sure. Okay. So let's see. We can come back to this. So let's see the possible examples of what trajectories of what might happen. So nothing is around, then this first term is the only one dominates. You don't have any interactions with other particles. So you just go straight to the destination. And you go with the maximum possible velocity because the velocity cannot be greater than 1. This is the first situation. The second situation, you have a red car which started from here, and the blue car started from here, and then the blue car goes to the left of red, and the red goes to the left of the blue. Okay. Blue trajectory. And so both of them go to the left of each other, right? So this is left-hand driving rule that they decided to use. Now here is another example where now you have the red car going, the red trajectory going this way, the blue trajectory going this way. And so they got puzzled because they wanted to go use a different driving traffic rules. They wanted to use different traffic rules. So it took them a while to resolve it. And basically at the end, this blue trajectory actually went to the right of the red trajectory because it's was able to do that. And this red trajectory actually had to stop for a while and figure out there is no way to pass to the left of the blue. And so it has to go also to the right of the blue. And so they had different perspective of what the driving rules has to be between them. But at the end of the day, they negotiated and decided that, well, we better stick with the same driving rule or otherwise we're not going to get to our destinations fast enough. Now, this is the third situation, is when 3 cars come together. And then eventually they may struggle in the beginning. They may have different traffic rules, left hand versus right hand. They negotiate and maybe use some seconds or so, but eventually they figure out that it's better to use the same traffic rule. So here they decided to use actually left hand traffic rule. So they went to the left, and then they discovered roundabout. Okay, they were not trained to know what the roundabout is. They were not trained to behave differently in the situation of 3 cars, 2 cars, or 4 cars. All this information is too much for them. Then why is it too much? Well, because there are only few decisions they can make. Steering wheel and accelerate brake. That's it. So lots of those different things are just irrelevant information, and only relevant information invariants are needed to figure out what to do. Okay, so now let's see a simulation, actually a movie, and then we can ask more questions. So it's only 1.5 minute long. So here, cars start with no prior training, so completely random initial conditions, and each of them separately trained. So they do not know that the other cars using the same architecture. There's like 50 cars or so, and all of them have different neural networks, and each of them individually trained. And so let's see. So for example, we can look at these two cars. Well, one slows down, goes. Now these two cars. See, they one had to give up and then like turn the other way. And then sometimes you see roundabouts right here, and there was a roundabout that was discovered. And pretty well, they are avoiding collisions and getting to where they should. Now, the way this program works is, as you see, there are no roads. What happens is that once the car reaches destination, it immediately gets a new destination to go to, and it goes there. And then it continues. Now, very difficult situation appear in the middle. And so to actually program all those situations and tell the cars how they should behave under those different conditions would be a nightmare. But we don't have to do this. And why? Because we do know that the number of relevant information has to be very small. It cannot be more than few. Why? Well, because there is only two possible actions you can do, position of a steering wheel and acceleration in the direction. So questions about either the simulations or about this possible trajectories?
So is the goal here to show that you can have this learning happen with very little information, just basically as long as you can capture the invariance of the environment?
That's right. That's the main idea. Now, first, we knew ahead of time that the relevant information is very small because there are very few actions you can have. Now, what are the invariants? What is the relevant information? Is a challenge. Figure out what is relevant, what is irrelevant. However, you can go it the hard way and just make your neural network learn, all possible situations, and eventually it will learn in the long run, maybe in thousands of years, it will learn what is relevant, what is irrelevant, or billions of years, I don't know. Or you can give a hint. And a hint comes from only considering invariants. Now, then the challenge is just figure out what are the relevant and what the irrelevant invariants. So we know the answer has to be few bits of information. We don't know what they are. And so the playground here is use your symmetries to figure out what the invariants are, and then show that that actually works. Now, it doesn't work perfectly. So again, if you go to this simulation, I'll run it once again. It doesn't work perfectly, and especially in the beginning, you see lots of situations where the car comes and brakes right before it collides, and presumably we haven't identified the right invariants, and there should be others, or maybe we can just add a few more invariants. At this point, the neural network is trained so fast because it's so tiny, it's so small, that there is no reason not to include other invariants. Now, as I said, there's lots of ways for you to generalize it. The technological layer was not implemented. The actual detection layer has to be also implemented. All those things. But the big idea, I think, is that there has to be lots of symmetries, and so make use of the symmetries that are there to construct your neural network. And other way around, do not impose symmetries that are not there. So don't impose symmetries on the neural network architecture if it is not part of the learning system. And that's why for this core of the neural network, we use unconstrained one. No constraints. The weight matrix decides for itself what it wants to do. Other questions? Let me just show you, I'll come back to ask you a question. Let me show how the loss function behaves here. Because what we can like take the loss function for all of the cars and try to see how it changes. And here it is. Now there's lots of training epochs here, and this is the plot of the same line, but on a different time scale. So here from 0 to 2000 time step of the activation dynamic. So 2000 times each car observed the environment, calculated the invariance, and then went through forward propagated obtain its desired position and velocity. And then once there, it's again calculated the loss function, and then calculated new invariance, again forward propagated to new position. It's kept doing this. So for 22,000 time steps, and each time step you can think about as a split second. So this is to calculate this, it's a minute or two. Well, no, it shouldn't be a minute, a few minutes, right? Because there's also the size of the car, and so presumably it will take you in the real environment. So let's say we implemented this 30 neurons network on the real cars, right? So we just say, all right, so let's assume that the technological layer problem was solved, the detection layer is solved, we put it in the real car, let it drive. So first, it will not behave well. Yes, it will try to avoid collisions, but it will not do it as smoothly. But eventually, and very fast, in a few minutes perhaps, well, depending how often it encounters difficult situation, it will learn. Now, this learning can be improved further if instead of having a separate neural network for each car, we would have had the same neural network for the car. But that would be cheating, right? Because then it would not be learning all possible other cars, but would be learning by knowing that other cars are exact copies of the car that is learned. And so you can really complicate things. You can intentionally put bad drivers in there and have it avoid that. And so inside of it, neural network would identify and say, well, the bad driver is actually a different type of drivers. And so I can early detect that it's a bad driver and put it in a different class and form different invariants with that driver. So all that's possible. But the main point here that goes exponentially fast to some asymptotic state, then it kind of learns and forgets things because, maybe first it was lucky enough. It discovered that there was a right and left hand driving rule, but maybe it eventually met some other car that didn't make the same choice. And so there may be some fluctuations. Eventually, all cars would have to discover the same hand traffic rule. And that's what happens with the loss. So in a very long time, it just fluctuates around some minimum. And presumably nothing better can happen with this architecture or with those particular invariants. And so if you want to do something better than that, then you have to add more invariants and work with them. Questions? So let me come back to this point. I think that was kind of important point, and now I'll state it more on the way that would be useful for developing physical theory. So here, all of the talk and most of the lectures that I given, I was saying, okay, here's what you can do with machine learning algorithms. But there's another important lesson that we learn from here, that sometimes it is more useful if you try to model the dynamics of the learning systems is or what looks like a learning system. Sometimes it's useful to use this learning idea, even if they don't seem like learning system. So for example, physical theories. If you can just have a physical theory, just like electrodynamics, we can look at it and says, all right, can I identify the loss function for which this invariant, let me see if I can go. Yeah, for which this invariant will be the relevant one. Can I identify it, that this will be a relevant? And then once I identify it, I will have a dual picture of electrodynamics. That would be, you can talk about this Lagrangian and electromagnetic waves and Coulomb force or Lorentz force, or you can say, well, no, electrons are just having this loss function. They're moving to minimize that and accomplish that task, etc. So that's one possible way. But I think even more interesting would be to apply it to biology, because in biology, we do have this agents, I don't know, ants or bees, who are trying to optimize some loss function, presumably. And they're kind of, wandering around trying to find what this loss function, we're trying to minimize it. But at the same time, we can just model them as agents, autonomous particles, and we can ask, okay, what would be the field theory description of their motions? what would be the field theory describing the particles, what would be it's like fermions, would be the field theory describing interaction between particles, would be like bosons, and how can we model it this way? And that would be interesting on itself. And presumably, like next time when I discuss biology, I will emphasize that. So once you identify that the learning dynamics is useful for modeling biological system, you can take it one step further and say, well, now that you know that, maybe you can look at the evolution of a large collection of agents, which can be bees, birds, or ants, whatever they are, and write down actually Lagrangian field theory description of it. And that would be the second view that we are advertising here. So learning view is just one view, and it may be useful to identify the loss function, but maybe the other view would be useful to identify the physical Lagrangian description of the system. And that can go back and forth, right? So once you've identified what the loss function describing the behavior of some physical or biological systems, you can write it in Lagrangian way, or you can do other way around. You can, if you identify the right Lagrangian description, maybe you can add the right invariance to your self-driving cars, which are not there. We were not there. So I was not able to write, maybe the choice for the invariance that was written was okay, but maybe it can be improved further if we identify what is the right field theory that described that. So that's the emergent part of that. So the main point here that those two pictures are dual and they can help each other. You can use physical picture to develop algorithms, and you can use learning picture to develop theories of whether it's physics or biology or whatever. Are there other questions?
I think I'm a little confused. How would you go from, say, like, so you have data on how ants move, and then presumably you have a neural network that learns, like replicates their movement. So you have a set of agents, kind of like you have here cars, that will learn the same sort of movement. But like, how would you go from that to
Right.
discovering
Good.
the loss function?
Right. So once you have the loss function, so whether it's ants or your cars, or you just observe how all of the cars move. Once you have that, you have to identify. Once you have that, you have identified already the invariance. Yes. So once you identify the invariance tell you what kind of fields there are.
I see. Okay. Yeah.
So that's kind of the. I mean, I keep. Yeah. So this is the key, right? Because once you have that. We put it other way around. We know which invariants, which Green's functions to correspond to which fields. Now you figure out those Green's functions or those invariants, and now we know what kind of fields there are. But maybe you're missing some. So maybe the field theory will tell you, well, no. You included this invariant, but the other was missing, and you should also have that as well. So here's a good example. So you might have identified that field E is useful, but the field theory is not written just for E. There has to be B. Okay, and then you would have, okay, no, I forgot one more invariant because of that, and so you will include that as well, and have that. So playing both ways is useful. So as you start with the neural architecture, you already define the invariance, you know what your Green's functions are, you know what the field theory, and then we may end up saying, okay, I know some of it, but not all. So let's go back and now add something, and then you go both ways.
See, so it's more of a recursive process where you keep adding invariants intuitively or from observation until you can replicate or mimic the system you're trying to understand. That's right,
but how do you add this? So this is something I said on this previous slide. Adding invariants, I think I'm probably I convinced you. You have to look at the invariants because nothing. If it's not an invariant, it makes no sense. But which invariants? That's the difficult question.
Right.
And then you say, okay, well, they may come from considerations of the underlying effective emergent field theory. And if they do, then kind of field theory will tell you what kind of invariants to add, and they will assist you in developing your theory further. But sometimes, like for example, in what we did here, So those invariants. So you see power of 3 here and the power of 4. Now, again, you would not have guessed that it has to be a power of 3 or power of 4 here, but we can show that it cannot be larger than 2. Why? Because then this invariant would be divergent, and then your car will just freeze moving. So things like that, things that come naturally from field theory prescription, that this will happen, may not come as easily from the point of view of just identifying invariants. So I think there's you have to use both pictures. In the best case, you have to use both. So with one, you can just try to by brute force adding those invariants, and the other you always use your field theory perspective, seeing which may or may not work.
Mm-hmm.
Okay, other questions? Yeah, so this is the, of course, work in progress, and but I guess the main message was that A, invariants are useful, and B, the invariants that you want to find can be easier identified if you have an emergent field theory picture in mind, which was trivial to do here. But of course, the search for what are the right invariants for the self-driving cars, the search continues. Those work pretty well. Doesn't mean that others shouldn't, especially when you add more cars, right? So you have more different cars, more different particles, and so a lot more different interactions. And so the problem does become messier, but at least we know how to tackle it. Okay, so I think this is it. So next lecture, we'll talk about biology. And again, the message will be, you can play around with your machine learning tools and trying to guess what the right architecture is and use the results that we've been calculating over this 9 lectures. Or sometimes you may just use hints from nature. One such example was in lecture 6 when we discussed the buy-in spread algorithm, but there is a lot more that nature can discovered. The other thing was today, so nature discovered the symmetries are useful, field theories are useful, but maybe there is more. And so we'll the next lecture will be about that, trying to see how biology can be described through this framework of learning. And if so, then you can go one by one through the biological phenomena and say, well, when and how those phenomena may be useful in actually developing machine learning algorithms. So that will be the topic of next lecture. Thank you.